Okay, so welcome back after the break, and today we will pick up from where we left off before the break and continue with game theory. So first we will study with mixed strategies. So first let us revisit the example of the price war that we discussed in the week before the break. So the price war game is a zero sum game, and so there are two companies X and Y who are the two players of this game, and they have two possible pricing strategies, selling their items at $1 or at $2, and if both of them sell at $1 or $2, they do not gain or lose anything. And if one of them sells at $1, the other sells at $2, then the one which sells at the lower price gains $5,000. Okay, so this is the payoff matrix, and notice that the entries of the payoff matrix here is not it's not pairs, right? Because every entry is just a single number; it's not a pair of numbers, and this is because the game is zero sum. So whatever one player gains, the other player loses. So here we have enumerated every possible strategy profile, the payoff corresponding to every possible strategy profile by just the payoff for the first player. So payoff for X. So in terms of pairs, in terms of the payoff written as pairs, you should read this as 5,000 and minus 5,000. So the first player gains $5,000 and the second player loses $5,000. Okay, so this is the expanded version to remind you. If you just look at this sort of a matrix, then this is the matrix of a zero sum game, and so this is the simplified payoff matrix, because for every entry of this payoff matrix you do not have a pair of numbers but just a single number, because the game is zero sum. So that is captured by the adjective simplified. And remember that as an entry of this kind of a payoff matrix is a saddle point if it is a minimum in its row and a maximum in its column. Okay. So for instance, if you look at 0, it's a minimum in its row and a maximum in its column. Okay. So at saddle points, no player wants to change, and it is an equilibrium. Because okay, so this is some of what we discussed in the last lecture. So now let us discuss a bit about crude analysis of games without saddle points. So in some sense, a game with saddle points is easier, because if you have a saddle point, then that already gives you a good strategy profile, because no player would want to change from that, right? So the tricky games are those games whose payoff matrix do not have saddle points. So consider, as an example, consider the following zero sum game with the following. So consider the following zero sum game with the following payoff matrix. So if player 1 consistently plays, so each player has two possible moves, move 1 or move 2, and so again this is enumerated by the payoff matrix is just it's a zero sum game, so the payoff matrix is just the payoff for the first player, okay, for the payoff for player 1. So of course if so the player 1 has two choices, move 1 and move 2, and of course if he plays move 2 and wins, he gets 1, right? Whereas if he plays move 1 and wins, it's like the returns are much higher, he gets 2. So of course there will be a natural sort of attraction or inclination to play the move 1. But the problem is that if the player 1 consistently plays move 1, then after some time player 2 will figure this out. He will notice. So if you are thinking of repeated trials of this game, so they are playing the game for many rounds, and the player 2, if the player 1 keeps on employing strategy 1, so if the player 1 keeps on using move 1 as his strategy, then after a point player 2 will notice this fact, and then he will adjust his move to move 2 if he was already not at move 2, and then the player 1 will actually end up losing, right? So you might think, so player 2 might think that, well, I have switched to move 2, and it really, player 1 losing means player 2 gaining, because it's a zero-sum game. So after having switched to move 2, player 2 might think that, okay, I have hit upon a really good move, so I'll just play this strategy. But if player 2 continues to play move 2 consistently, then player 1 will notice that after some point, and then he also will switch to move 2 when he will gain 1. Okay? So the point is that it is not beneficial for either player to keep on playing the same strategy. Okay? Because if it becomes predictable, then he is in bad shape. Because then the other player will adjust his strategy accordingly, and using the fact that this game has no saddle points, the other player will always have a choice of, always have the possibility of adjusting his strategy so that the payoff for the first player decreases. Okay? So in summary, it is not, if the game has no saddle points, then it is not a good idea to keep on employing the same strategy repeatedly. So, so what to do? So you can continue with this example just to motivate the probabilistic part which is coming very soon. So so far we have discussed player 1 consistently playing move 1 and then player 2 changing, but then if player 2 changes to move 2, then player 1 can notice that and he can change into move 2 also, right? However, now if player 1 keeps on playing move 2 continuously, so player 2 was at move 2, player 1 noticed that and switched himself to move 2. So now he is winning 1, he is getting a payoff of +1 at every round. And if he keeps on doing this consistently, then player 2 will notice that after some point and he will change to move 1 when player 1 actually loses 1. Right? His payoff is -1 and player 2 gains 1. So, but then if player 2 keeps on playing move 1, then player 1 will notice it and switch himself to move 2 when he will start winning $2 in every round. So this will keep on continuing. We have probably covered almost all the possible combinations, and we just saw that for any combination of strategies, if one player continues to play that strategy, then the other player can always notice that and switch the strategy and improve his prospects. Okay. So this kind of situation clearly calls for a new idea, and the new idea is that every player should choose at each play of the game a strategy at random. So now, even if there are repeated trials of the game, repeated matches of the same game, it's one player. I mean, the player, both the players are choosing their strategies at random. So his opponent, for example, is never sure which strategy he is going to pick the next time. So he cannot adjust. The opponent cannot adjust his own strategy accordingly in order to improve his prospects. Okay. So basically, this is the use of randomness. The random choice of strategy is precisely to introduce an element of uncertainty, a lack of knowledge, which was previously allowing both the players to update their strategies periodically, so that their payoffs can increase. Okay. So, this brings us to the concept, this brings us from the concept of pure strategy to the concept of mixed strategies. So, by choosing a strategy at random, say with certain probability, the other player has no way of predicting which strategy will be used. The problem for each player will then be to set these probabilities in an optimal way. Okay? So, by moving, so a pure strategy, if you remember, is a choice of strategy where you somehow you feel that a certain strategy among a possible choice of strategies is the best for you, and for repeated trials of the game, you just keep on playing that strategy. Okay? So, that is pure strategy. Mixed strategy is that at every trial of the game, you among your array of possible strategy choices, you pick one at random according to some probability distribution. So, for example, in this 2-player game, move 1 and move 2, it is not necessary that at random means you pick move 1 with probability half or you pick move 2 with probability half. Okay? You could pick move 1 and move 2 with any probabilities. So, move 1 with some probability p and move 2 with probability 1 minus p for any p between 0 and 1, and then so that also qualifies as a mixed strategy, right. As long as p is between 0 and 1, there is going to be randomness in your choices and it is going to confuse your opponent, so that he cannot just keep on adjusting his strategy accordingly. So, but now, so in the setting of pure strategies, we already saw quite a bit of discussion about how to work out the best possible choice of strategy, right. So, it brought us to the concept of Nash equilibrium, it brought us to the concept of saddle points and so on. But now that we have introduced randomness, the natural question arises as to, is there anything left to, is there any notion of a best possible strategy, right? Is there any notion of a best way of designing the choice of your strategy? So, this is, so what we will see is that in spite of using randomness, you still have the problem, you still have to tackle the question of how best to choose your strategy, in the sense that, so previously you had, let us say, 2 strategies possible, move 1 and move 2, and your goal was to decide whether it was to play, whether it was better to play move 1 or it was better to play move 2, right. But now that we have, so that is in the setting of pure strategies. In the setting of mixed strategies, you pick at any trial of the game, you pick move 1 with probability p and you pick move 2 with probability 1 minus p. So, you bring a coin with bias p, you toss that coin, if it falls heads, which happens with probability p, you choose move 1, if it falls tails, you choose move 2. But now, this has introduced a new variable in your problem, which is the bias of the coin. So, it's the probability of choosing move 1. So, this is now a variable, right, because no one told you what is the best value of p. So, now the question changes from the choice of the best strategy among a possible collection of strategies to the choice of the best probability distribution according to which you should pick your strategy, according to which you should pick your random strategy, so as to maximize your payoff. Okay. So, this is what we are going to look at. So, the problem for each player will then be to set these probabilities of choosing various strategies in an optimal way. And this will help us to solve zero-sum games without saddle points and variable sum games without dominance. Okay. So, let us take an example of a game of tennis. So, there are 2 players, call them server and receiver. So, they can play 2 moves, forehand and backhand, and the payoffs are as outlined below. So, this is not a zero-sum game. So, you can see that the payoff matrix, every entry of the payoff matrix is a pair. the first coordinate of this pair is a payoff for the receiver, the second coordinate is the payoff for the server. Okay? So, this is the convention. So, now we will analyze this game in the context of the discussion that we just had. So, the key insight of the discussion that we had over the last few minutes is that in games without some obvious base strategy, one should mix up one strategy randomly, that is, make a random choice of strategies at every turn of the game, so as to surprise your opponent. Okay? So, if you have R possible strategies available, so in the game of tennis or in the game with move 1 and move 2, R was equal to 2 because every player had 2 strategies available. So, if you have R strategies available, then you can call them strategy 1, strategy 2, strategy 3, blah 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 up to strategy R. So, you have to decide the probability with which you should pick strategy J, where J lies between 1 and R. So, strategy J is one of these possible strategies. So, let us call that probability Pj. Okay? So, you pick strategy J with probability Pj, and since you have to choose some strategy, so the Pi's, the Pj's should sum to 1, right, because you are choosing some strategy with probability. So, it is a probability distribution. The P1, P2, PR are forms of probability distribution over the set of strategies. Okay? So, this is called mixed strategy. So, this is exactly for R equal to 2, this is exactly the example of move 1 and move 2, where you are choosing move 1 with probability P and move 2 with probability 1 minus P. So, in this notation, it should be P1 and P2, move 1 with probability P1, move 2 with probability P2, but notice that P1 plus P2 in that case would be equal to 1, so P2 has to be 1 minus P1 anyway, right. So, everything tallies. Okay. So, in the example of tennis, you can check that it has no Nash equilibrium in pure strategy. So, you can just use the definition of Nash equilibrium and check for every strategy profile, and you will see that there is no strategy profile which satisfies the condition of Nash equilibrium. So, let us say, we will abbreviate forehand by F, backhand by B. So, let us say the receiver uses F with probability P. So, 1 minus F will be, so B will be used with probability 1 minus P. Similarly, server will choose F with probability Q, and therefore B will be used with probability 1 minus Q. Okay? So, remember that now, remember that P and Q are now quantities to be determined, and now the whole game and now the whole issue has shifted to finding the best possible choice of P and Q, so that the P-offs are maximized. Okay? In a game of tennis, which has, okay. So, we have thus expanded the set of possible strategies. So, each player now has a set of strategy given by P in 0 to 1. So, let us think of the receiver. So, receiver has a set of strategies given by P between 0 and 1, because every choice of P gives the receiver a different strategy, right, because he will be mixing up the forehand and the backhand in different proportions. So, for every choice of P, the receiver has a different strategy, and so you can think, so if this is the receiver and this is the server, so the receiver chooses some P between 0 and 1, the server will choose some Q between 0 and 1, right? So, if receiver calibrates his strategy by a particular choice of P, which is the proportion of choosing forehand in the interval 0 to 1, the server will similarly calibrate his strategy with a choice of Q, which is the server's proportion of hitting forehands. Then you can imagine that the strategy is now described by this point P comma Q, P for the receiver, S for Q for the server. And P can range anywhere between 0 and 1, Q can range anywhere between 0 and 1. So, geometrically, this is, you should pardon my drawing abilities, imagine that this is a square. It looks more like a rectangle, I understand that, but it's a square. So, 0, 1, 0, 1, and so this is 1, 1, and P and Q lie somewhere in between. So, this is the unit square, if you may recall, and the strategy profile is now calibrated by a point in the unit square. And since P and Q can range anywhere between 0 and 1, all possible points inside the unit square, 1 by 1 square, are valid. Right? So, the strategy profiles for the two players are in one-to-one correspondence with the points inside the 1 by 1 square. Okay. So, now given that the strategy is a random, so now the question naturally arises as to how do you measure the payoffs. Okay. So, what we will do, so what is the convention in the field is to measure. So, of course, if you choose your strategy randomly, you cannot just read off your payoff from the payoff matrix, because you are choosing your strategy randomly. So, there is no entry in the payoff matrix which corresponds to your strategy, because your strategy is random, right. So, what do you do? So, think of the receiver. Okay. If the server plays forehand, then the receiver gets payoff 4 with probability P, and so this is P, this is 1 minus P. If the server chooses the strategy forehand, then receiver gets payoff P, gets payoff 4 with probability P, and payoff 2 with probability 1 minus P, right. So, if you fix the choice of strategy of the server, then you can calculate the mean of the payoff for the receiver. Again, if you fix a particular pure strategy, forehand or backhand, either forehand or backhand, if you fix a choice of a particular choice of a pure strategy for the server and hold it fixed, the payoff for the receiver is still random, because the receiver himself is fluctuating between the two choices of strategies. So, the payoff for the server, payoff for the receiver, even though the server is fixed at a particular pure strategy, the receiver, his payoff for the receiver is still a random variable, but you can calculate the average or the expected payoff for this random variable, right. So, you can calculate the expected value of this random variable and use it as a representation of the payoff, which the receiver can expect if the server plays forehand. Similarly, if the server plays backhand, you can also calculate the expected payoff for the receiver. So, if you fix the strategy, choice of strategy of the server to be backhand, then again the payoff for the receiver will be still random, because the receiver's own choice of strategy is randomly fluctuating between forehand and backhand. But for this random variable, you can compute a single number, which is its mean value or expected value. And this is the value which the server can, which the receiver can expect to get as payoff when the opponent, that is the server, plays backhand. Okay. So we have to calculate the expected payoff for every of these possible fixed choice of strategies of the server. So for this you get, for this column you get an expected payoff for receiver. Similarly, for this column you get an expected payoff for receiver. Of course, these two expected payoffs will not necessarily be the same. In general, they will be different, right? And both of them will depend on P. So both of them will depend on P, right? So these two expected payoffs will be different, and our goal would be to choose the strategy profile which maximizes the worst among these expected payoffs. Okay? So we will see the details of this kind of a analysis through an example. So let's calculate the expected payoffs. So if the server plays F, then the expected payoff for the receiver, so we are taking the receiver's point of view, we are analyzing the game from the receiver's point of view at the moment. If the server plays F, the receiver, his expected payoff is 4 with probability P and 2 with probability 1 minus P. So you can calculate the mean or the expectation of this random variable and you will get 2P plus 2. So notice that for this, in this case, that is for this column, so when the server plays forehand, the expected payoff for the receiver increases with P because it is 2P plus 2. Now let us consider the case when the server plays backhand, so we are in this column. Again, the expected payoff is, so the payoff is 1 with probability P and 3 with probability 1 minus P. So the expected payoff is 1 times P plus 3 times 1 minus P, so 3 minus 2P. So this is the expected payoff. And notice that both of them depend on P. In both columns the expected payoff depends on P. Because P is going to be, we have to choose P, right? So we have to choose the best value of P. So naturally the expected payoff will depend on P. So notice that in this column, unlike the previous column, the expected payoff decreases with P because it is now 3 minus 2P. So if P increases, 3 minus 2P decreases. So here is the conundrum. If you look at the first column, then of course the expected payoff increases with P. So you would really love to take P to be large as possible. But that will work in your favor only if the server plays strategy F. As soon as it plays strategy B, this is going to harm you in a very bad way, because when the server plays the other strategy, that is B, your expected payoff actually decreases with P. So for that strategy, for that strategy choice of the server, the receiver would actually like to choose the probability P to be as small as possible. Okay, choose the parameter P to be as small as possible in order to make his payoff the largest, expected payoff the largest. But the point is that, but the conundrum for the receiver is that he doesn't know in advance whether the server is going to play F or play B. If he knew, he would be in great shape, but he doesn't know. So he has to choose P in such a way that he is okay in both cases. Okay? So that's the goal. So then the question is right balance, because P large, first case very good, second case very bad. P too small, second case very good, first case very bad. So P has to be balanced in some way, right? So how do we find the right balance? So, okay, so the right balance will be found by plotting some graphs and solving some simple equations, but we will discuss the finding of the right balance after a 10 minutes break. So, we will meet after 10 minutes. Okay. So, let us get back to the question of finding the right balance. So, before the break, we discussed the game of tennis and we were analyzing the game from the point of view of the receiver. So, we noticed that for the, if the server chooses to play forehand, then the expected payoff is 2p plus 2 for the receiver. If the server plays backhand, then the expected payoff for the receiver is 3 minus 2p. So, one of these expressions is increasing in p, and therefore, it would be good to have a large choice of p, whereas the other expression is decreasing in p. So, it would be good to have a small choice of p, but the receiver doesn't know for sure which option the server will exercise. So, he has to somehow strike a balance between the two choices, small choice and big choice of p, so as to get the optimal payoff. So, so the question is, what is the right balance in terms of p? So, so this is the, so to understand this, let us draw a picture. So, this is the payoff. So, this curve is a payoff if the server plays f, and this curve is the payoff when the server plays b. So, so as usual, as we already noticed from the algebraic expressions, the first curve is increasing in p and the second curve is decreasing in p as you vary p in the interval 0 to 1. And now, so the question is, what is the right balance? So, you notice that since these two are increasing and decreasing, these curves will intersect at some point, right. So, this intersection point has somehow, it has a natural appeal, some curve is increasing, some other curve is decreasing, you want to balance them. So, the intersection point intuitively has a natural appeal. And now let us see why, in terms of the mathematics also, it's a very useful value of p to have. So, the point is that if you, so let us first solve for the intersection. So, what is this intersection value? So, what is the value of p? Let's call it p star, which gives you the intersection. So, 2 plus 2p, this curve should be equal to 3 minus 2p, which is that curve. You solve for this. So, this is 4p equal to 1. So, that is p equal to 1/4, which is 0.25. So, p equal to 0.25, and you can calculate that for that value. So, that is the p coordinate. The payoff is, you can, to calculate the payoff corresponding to p equal to p star, which is 0.25, you can just sub p equal to 0.25 into this equation and get that the payoff is 2.5. Okay. So, if p star, if the server chooses the value p star for mixing his forehand and backhands, then his payoff is playing, if the opponent plays f, then the payoff is 2.5, right, because this point lies on the increasing curve. But if the opponent plays the backhand, even then the payoff is 2.5, because it is also this point is also lying on the decreasing curve. So, that is the benefit of choosing p star to be the value corresponding to the x coordinate of the point which lies at the intersection of these two payoff curves, because no matter what strategy the opponent chooses to play, your payoff will always remain fixed at the same value 2.5. Okay. So, that is already a good property, right, that you do not really have to worry about fluctuations in your payoff if your opponent changes the policy, changes his strategy, because you are assured that no matter what the opponent does, your payoff is always, your expected payoff is always 2.5. Okay, that's good. That's a good property. The receiver, now what will happen if the receiver uses a mixed strategy? So, if the mixing parameter for the receiver, that is P, if he chooses a value less than P, what will happen in that case? Well, if he will actually gain in terms of expected payoff if the server chooses to play backhand, because if P is smaller, if you take P here, which is smaller than P star equal to 0.25, of course, for the second curve, the payoff is higher than this level. So, the payoff will be somewhere here. So, higher than 2.5, but that is only if the server plays backhand. The server can switch his strategy to forehand, and immediately your payoff will actually drop below 2.5, right. So, if you employ a mixed strategy with parameter P, which is smaller than 0.25, and do it over many turns of the game, then your opponent can figure that out, and he can switch his strategy to backhand, and immediately for that value of P, your expected payoff will drop below 2.5. So, you are going to lose. On the other hand, if the receiver sets P to be bigger than 0.25, which is his mixing parameter for the choice of mixed strategy, the server can again, if you are playing, so if you are choosing P here bigger than 0.25, so you are hitting forehand with probability P, which is bigger than 0.25, and backhand with probability 1 minus P. So, if you do it, keep on doing it, then your opponent can sort of observe your game and calculate the he can calculate the frequencies of forehand and backhand, and from there he can pretty much figure out that you are hitting forehand with a proportion P fraction of the time, and we are hitting backhand with probability 1 minus P, right. So, once he figures that out, he will immediately look at this curve and switch his strategy from forehand to backhand, and immediately the great benefit, the great payoff you were getting under the strategy F from your opponent will drop to a much lower payoff than 2.5, because your because your opponent will immediately switch the strategy to B. So, once he figures out by calculating the frequencies that you are hitting forehands with probability P, which is bigger than 0.25. However, so the parameter, so if you deploy the mixed strategy with parameter P bigger than 0.25 and continue deploying it repeatedly over many iterations of the game, many trials, many turns of the game, eventually you are going to lose, right? Because your opponent will figure that out and switch his strategy accordingly, so as to push your payoff, so as to push your expected payoff down. However, only when you choose P star equal to P star equal to 0.25, the opponent cannot do anything to push your payoff down below 2.5. So, this payoff you are always guaranteed. Okay? Any questions? So, at the critical point P equal to 0.25, so if P bigger than 0.25, then the server can exploit that and serve to the backhand all the time, giving the receiver the lower of the two payoffs. So, this is what we discussed in the context of this diagram. And at the critical point P equal to 0.25, the receiver's payoff is the same, namely 2.5, regardless of the server's actions. So, this is the notion of indifference. So, this is an important concept, the notion of namely the notion of indifference. The receiver has found a strategy that is taking P to be 0.25, which guarantees him a payoff of 2.5 regardless of what the server does. So in that case, we say that the receiver is indifferent to the server's actions. And if the receiver deviates from this strategy, then the server can exploit this misstep and adjust his own strategy so that this results in a lower payoff for the receiver, and hence a higher payoff for the server, since this is a constant sum game. So the sum is always constant, the sum is always 5. So so it's not zero sum, but still, because the sum of the payoffs is always constant, therefore if the receiver's payoff goes down, the server's payoff will go up. Okay. So in summary, by choosing p equal to 0.25, the receiver is indifferent to the server's actions. If the receiver deviates from the strategy of choosing p equal to 0.25, the server can then adjust his strategy accordingly, which will result in a lower payoff for the receiver. Okay. So now let us look at the game from the server's point of view. So this should be server. Okay. Server's point of view. So from the server's point of view, he chooses forehand with probability p, backhand with probability forehand with probability q, backhand with probability 1 minus q, and the question is, what is the optimal value of q? So now let's go through the yoga and do a similar analysis as we did for the server. If the receiver, which is his opponent now, plays f, then the server's expected payoff is, so the second coordinate is the server's payoff. So it is 1 times q So if the receiver plays forehand, then the server's expected payoff is 1 times q plus 4 times 1 minus q, right? Because he plays forehand with probability q and backhand with probability 1 minus q. So this is 4 minus 3q. If the receiver plays backhand, then the server's expected payoff is 3q times plus 2 times 1 minus q. Okay? So this is 2 plus q. Again, you can plot these two payoff curves and notice that if the receiver plays backhand, then it's an increasing curve in q, as the payoff is the expected payoff is an increasing curve, increasing straight line in q, as q varies between 0 to 1. Whereas if the receiver plays forehand, then the expected payoff for the server is a decreasing function in q. So again, you can do the same yoga and focus on the intersection point, which is the sweet spot, and solving for the intersection of these two straight lines, you will find that q is equal to 0.5. So at this point, the payoff for the receiver, for the server, you can calculate by plugging in q equal to 0.5 here, for example. The payoff for the receiver, payoff for the server is going to be 2.5, and at this point the expected payoff for the server is 2.5 regardless of what the receiver does, right? Because if the receiver chooses backhand, even then for q equal to q star equal to 0.5, if the receiver chooses to play backhand, then even then the expected payoff is this value, which is 2.5. If the receiver chooses to play forehand, even then for q equal to q star, you plot it on this line and you will get a value of payoff of 2.5 for the server. So again, the server is indifferent to the receiver for the choice of q, which is q star, which is 0.5. Okay. So now, if the server, if the receiver chooses to play p, which is p star, which is 0.25, and the server decides to play q star, which is 0.5, then each of them is indifferent to what the other player is doing, and at that point the game is fair, because we just calculated that if receiver plays P star, which is 0.25, and server plays Q star, which is 0.5, then the payoff for both the players is 2.5. Okay? So it's a fair game. So is there any incentive for either player to deviate from this strategy profile? The answer is no. There is no incentive to change. Why? Because if one particular player changes, that is, changes the value of P or changes the value of Q, the other player can exploit that and adjust, choose the curve accordingly, choose the forehand or the backhand curve accordingly, so as to lower the expected payoff of the first player and therefore improve his own expected payoff. Okay? So thus, the strategy profile PQ, which is the mixing probabilities of 0.25 and 0.5 for the receiver and the server respectively, there is no incentive for any of the players to change. So therefore, it is a Nash equilibrium in mixed strategies. So this is called a Nash equilibrium in mixed strategies. No player has any incentive to change. So let's take another example, which is the game of matching pennies. So two players, there are two players, player 1 and player 2. Both of them toss a coin. If the result of both the coins is the same, that is, both are head or both are tail, the player 1 wins one and the player 2 loses one. But if the outcomes of the two coins are different, then the player 1 loses 1 and the player 2 gains 1. Right? So if the pennies match, then player 1 wins. If the pennies mismatch, then player 2 wins. So you should think of this as a game of strategies, in the sense that the players are not really tossing a coin, but both the players have a coin each, and they can sort of put the coin on the table either with head facing upwards or tail facing upwards. That's their choice of strategy, head or tail, H or T. And if the two coins match, player 1 wins, and if the two coins happen to mismatch, player 2 wins. So in terms of mixed strategies, that is when the player 2 both the players want to sort of pick randomly between the two strategies of heads and tails. Let's think of the situation when player 1 mixes heads and tails in the proportion P and 1 minus P respectively, and the player 2 mixes heads and tails in the proportions Q and 1 minus Q respectively. So let's find the Nash equilibrium. So from player 1's point of view, so we are analyzing the game from the player 1's point of view. If the player 2 plays head, then his payoff is 1 with probability P and minus 1 with probability 1 minus P. So its expected payoff, if the player 2 plays head, is P minus 1 minus P, which is 2P minus 1. So this is if the player 2 plays head. If the player 2 plays tail, then the expected payoff is minus 1 with probability P and 1 with probability 1 minus P. So this is 1 minus 2P. So again, you can plot this kind of curves and find the point of intersection. So you can solve for the point of intersection, the right value of P, by setting the two payoffs for the two possibilities to be equal, and then you will get the optimal value of P to be P star, which is 0.5 in this case. Similarly, you can, so this is analyzing the game from the player 1's point of view. You can do a similar analysis of the game from the player 2's point of view and obtain the optimal value of Q, which is Q star, which is 0.5. So thus, the game of matching pennies has a Nash equilibrium in the mixed strategy at the optimal value PQ, which is P star comma Q star, which is 0.5 comma 0.5 or 1/2 comma 1/2. Okay. And in some sense, some of you might intuitively expect this because the game is completely symmetric between the two players. So, probably the point of symmetry of the square. So you think of the square as 0, 1, 1, and 1, 1. So the center of the square is basically 1/2, 1/2, and indeed it is the most symmetric point inside the square, and this is exactly where the Nash equilibrium is being attained. Okay. Okay. So this is what we had to discuss today about mixed strategies. So at this point we would like to break for today, and we will continue next week. Okay. I mean, sorry, in the next lecture.